Welcome to the second part of climate variability and predictability session. We have 4 presentations here, followed by 15-minute discussion. Our first speaker is Professor Qinghua Din. He will give a 30-minute invited talk on enhanced jet stream waviness induced by suppressed tropical Pacific convection during boreal summer. So Qinghua, please.
Okay, thank you. Yeah, I will share my screen. Yeah, I think everyone can see my slide. So really appreciate invitation from the chair, Bing and Ling Hai. The first thing I want to apologize. I missed the first part of this session due to this time difference. But I read the abstract. It seems like there's 4 very interesting talk given by like the very good scholar working on this field. So I'm really happy to continue the same line of discussion on this topic to see how we understand better this the AA article amplification effect on this mid-latitude waviness or like extreme event occurrence. So this is a study that basically I want to focus on the summertime. And this is the work collaborate with my collaborator and my student at UCSB and the different institute in the United States and China. The main goal here is to provide a little bit different perspective to this phenomenon, just like the enhanced waviness along this mid-latitude jet in boreal summer, because we know right now this is a hot topic and still under like debate. The main argument is that the AA Arctic amplification due to the global warming can weaken the temperature gradient from the tropical region to the polar region. And once the jet is become wavier, many people think that probably the wavier jet will regulate the activity of the weather activity propagating along the jet. So this is really a hot topic and it's an important topic. If this effect, this mechanism really works, and probably this means that AA cannot be the AA effect cannot be only confined in the polar region, and also have some like a knock-on effect to the like a region outside the polar. So I think probably in the first part of the session, the speaker already gave a really good review, so I try to make it's part short. This introduction part very short. So we know the AA can either shift or weaken the jet. So there's probably 2 possibilities of the mechanism. The first one is changing the gradient from north to south, and once the jet become wavier, and there's prefer to induce the temperature like the warm and cold intrusion from north to south or from south to north. And the favorite is the well mixing of the temperature between the 2 areas. Another argument is that once the tropical warming due to the global change favor expansion of like the ITC or expansion of a tropical zone, that may favor also like the subtropical jet move upward. And so there's 2 type of argument. Just like one thing is a change of gradient, but another one is a change of position of the 2 jet. And the Arctic warming favor equator shift of the subtropical polar jet, but like a tropical zone expansion favor this polar movement of this subtropical jet. And but we know this phenomenon is signal dependent, because as we know, most of the study, I believe this is the first type of study mainly focus on the winter time, because they believe this effect may be more prominent in the winter time, since the A effect is the most important or more apparent in the winter. And but the stratosphere, like the first talk given, like the first part, like by Judy's recent work, this polar vortex is really important, and the favor is the like the first late like a wave of probably upward and then going down, and there's some delay, and there's a polar vortex change through this stratosphere, troposphere stratosphere feedback can influence like the climate over like Eurasia, interior of Eurasia, or like interior of North American continent. But a recent study by this PAMIP polar amplification model intercomparison project has shown that model, if false by this AA effect, cannot well or fully capture some like the linkage we are observing from the real world. So this is still really some issues that we should be paying more attention. Just why model and real world or observation show different feature of this linkage. I think that it's still open question. So it's to me is we still need to do more to understand this issue. But summertime, a recent paper by Cohen, by Kumo in 2018-19, they also propose this AA can influence this summertime jet stream through three possible mechanisms. The first one is still like the same idea, just the weakness adjust the temperature gradient from north to south, and weakness the storm track, and regulate the activity of a storm track. And another one is like the jet shift, right? And like the two jet may stay closer due to this expansion of the polar region, also tropical region. So that make our understanding, complicate our understanding of how jet will respond to the Arctic amplification and the tropical warming. The third one is still like once the jet become weaker, probably is the some quasi-stationary wave train will become more sensitive to like the heating generated somewhere in either in polar region or tropical region or even along the jet stream. So this is a new topic, still very new topic, I think, and we still need to understand the cause of the waviness and rely on our model and observation data. But we know observation data is relatively short because the best or reliable historical data, I mean the reanalysis is only probably give us like a 40 years observation since 1979. And the model we can use a model for look at the longer time series or longer data, but the issue is that how reliable model is to aid us understand this issue. So here is the model output I generate in my another paper with my student. So you can see here is that we looked at the annual mean field, and we looked at three different variables. One thing is Z200. Here Z200 means the potential high at upper level, 200 millibar. So this is a simple observed from ERA5, 40 years, a trend annual mean field. And this is the same field from CMOS 5, historical run, and from like a 30 model average. And this is a 5 large ensemble. So each large ensemble contain around like a 40 to 100 members. So total here is like a 200 members, but from five climate model, add them together. And because it's a historical run, if we add them together, the main thing we see here is like the model respond to historical or anthropogenic forcing. So we can think this is the model response to CO2 increase in the model, and this is observation. And this is the middle level circulation, 500 millibar to potential high. We call it a Z500, and the same variable, but from model world. And this is surface temperature observation from ERA5 and from this the model world. So you can see this is 40 years the trend of the three variable to anthropogenic forcing in model, and this is in reanalysis. So what I want to say here is that if you look to just simply compare this, if we just simply do like a domain average or global mean average, probably we will see the models do really well to capture like observation. But if you look at the spatial pattern, we find some contrast between observation, reanalysis, and the model. The first contrast I want you to pay attention is that the model the potential high increase the most in tropical region, right? Both model in sample show the same thing, but observation show less increase. There's some increase, but less increase in the tropical region than in the polar region. Another thing is that in observation, there's a really strong Arctic warming. We know it's Arctic amplification. Model also generates Arctic amplification effect, but not as strong as observation. Another thing is the model favor El Nino-like warming in this CMOS 5, but the model, the observation shows something like no change over Eastern Pacific. Some people think this is probably due to the PDO or IPO or part of the IPO over like the recent 40 years of the variability, and model generally some like El Nino-like. Another one is over like the Southern Ocean, like the West Antarctica. There's a negative like a decreasing of the potential high, but the model doesn't get this. I think this tells me something like the model response to CO2 forcing is very different from real world, because in real world is something like a barotropical structure. The maximum warming at the surface, but also maximum warming at the potential high upper level. That means the entire air column increase in Arctic. But in the model world, it's something like a baroclinic feature. The surface is pretty warm, but upper level is not like that strong, right, as observed. And in the model, it's more like the increase of potential high in the tropical region, because this is determined by this moist diabatic heating profile, right, like the lapse rate feedback, something like this. And this less increase in the tropical region in real analysis indicates something due to this probably the IPO cooling trend, because during this recent 20 years, 40 years, the IPO favors a cooling trend over Eastern Pacific, and this can offset some tropical warming by the global warming and weaken this increase of this height increase in the tropical region. So all this tells us that we can not only consider the model response or the climate response to anthropogenic forcing, we should also consider something we call the tropical SST variability, especially over the Eastern Pacific, because we know over that place, the SST variability could contain some variability longer than ENSO, like a typical ENSO like the time scale, maybe longer than like a 10 to 20 years, and also may last for like a multi-decade. But then if we look at the 40 years trend, this feature can imprint some signal on this long-term variability. So this lead to our goal, is that the goal of my study is that to understand the different climate driver of this waviness. That is means like the internal tropical acidic forcing, something like the PDO phase or IPO phase, and how the forcing relate to this tropical forcing versus that due to the Arctic amplification. And so we will focus on this 42 years from 1979 to 2020 in summertime, and using ERA5. We try to emphasize that probably something we have observed over the past 40 years. Part of them is due to this IPO related signal, and due to something we call like a tropical teleconnection effect. So this is a very classical idea proposed like a long time ago, and like a tropical forcing can generate a wave train, and this wave train prefer to propagate to the high latitude and generate some signal there to regulate the storm track, and also generate some like a climate anomaly over the region. So this is our the first plot in our study. So you can see we have like a 6 plot plus a zonal mean panel to the right. You can see this is the observation again, JJA Z200 upper level potential high in observation, just a simply ERA5. So we look at this, you can see, yeah, indeed, over the past 40 years, the jet stream become more wavy. And you can see this a number of high pressure center over is just to stay along this jet. And to better show this, the waviness, we remove zonal mean component. So this zonal mean component is shown in this D panel. So this is a zonal mean Z200, just simply do zonal average along each latitude. So we show here, so you can see over the 40° north and somehow 30° south is a maximum increase of this zonal mean potential height. After we remove this zonal mean component, we can see very clearly there is a waviness increase. We call it the non-zonal Z200. So there's like a wave number 5 to 4 structure, high-low structure. So if you see clearly, there's a low, 1 low center, 2 low, 3, 4, 5. So 4 low pressure center. So that means the wave number is around wave number 5, zonal wave number 5, or zonal wave number 6. And if we look at the V200, that's a simply Meridiano wind 200. We don't do anything on this. We feel just like a simply show the trend in JJA. You still can find this enhancement of this like the Meridiano wind along the like jet stream over is a 40° north. So this indicates that indeed the wave feature is enhanced over past 40 years in summer. And if we look at the temperature, ocean temperature, SST temperature trend, this is the raw trend, just a simple JJA trend. And to to reduce or minimize this global warming impact, we remove a global warming signal, just a global warming, the global mean average SAT from this field. We call non-global SAT. So you can see, we can somehow see more clear is like a cooling signal over Eastern Pacific. And also it's a precipitation, just a raw precipitation trend in JJA. So there's a draining trend here. So this indicate over past 40 years, but the ITCZ become drier over the 30 years, and because probably due to this ITCZ or due to this IPO like a cooling over the 40 years. But on top of this signal, global warming generate like a warming almost everywhere. And meanwhile, along the jet, the jet stream become more wavy, and show like the wave number 5, wave number 6 structure. And so I also want to say I want to link this waviness to something the mode have been identified like 15 years ago by my study. We call it circumglobal tidal connection. In that study, we show like there's over the same region there exists some like a wave train like a leading mode tidal connection we call the circumglobal. This mode also favor wave number zonal wave number 5 to wave number 6 structure with something like a high-low structure. And we have some mechanism to explain this establishment of this wave train structure, just like the some like the two-way interaction with the Indian monsoon, or like due to this like the tropical instability around the jet axis region or Atlantic. And but if you compare this structure with this trend non-zonal Z200, you can find a pretty good similarity between this structure, but just to change the phase, opposite phase. So this is high, 5 high center, or is a location. But if you look at the trend, it's a low center. So this we think that probably in observation, something we observe is due to the trigger of this internal mode by some like a tropical forcing. So then we want to check the model, how model captures the similar feature, observe the feature if model only forced by CO2 forcing. So this is the historical run from different like ensample. So this is CSM1 large ensample, 40 member historical run over same period and the same variable. You can see the raw trend Z200 remove non-zonal component put here, and just simply V200 and the precipitation and SST. You can find if we just do the non-zonal component, the magnitude of the trend non-zonal component is much weaker than observation. Here we're using different time scale because if we're using the same scale, this is really weak. So here it's like the -3 potential height limiter, right? In observation, it's more like some -10, -12. And the wind also show much weaker magnitude than observation, but to show some feature like a waviness, especially over Eurasia, but not over Pacific, like the North Pacific and Atlantic. And the most interesting thing is that a model generates increased precipitation in the deep tropics, in the deep tropical Pacific. But in observation, we know in over the past 40 years, there's like a little bit like a draining trend over the same place because it's an IPO fix. But a model, as we know, model always favor like El Nino-like pattern. So El Nino-like pattern favor increased precipitation over like a deep tropical Pacific. So this is CSM1 model tells us, and this is the main component. You can see the red one is a ERA5, and the model always overestimate this zonal mean height increase, especially in the tropical region, because we know the model prefers the moist lab straight type of a response. But in observation, there's IPO like, so that can offset this tropical response to anthropogenic forcing. We also check a CMOS. We find a very similar feature as a CSM large ensample. Wind is not strong as observation, and meridional wind trend is not strong as observation, and also increased precipitation in the deep tropics. And because it's El Nino-like pattern, we check this 30 model historical run, and we also check like the CMOS model is the most recent, latest generation of a model, 35 model. We find the CMOS to do a little bit better than the CMOS, can capture some waviness. And this patterns is also a little bit stronger or perform better than CMOS to capture the waviness. So that means that the waviness some part of waviness, observed waviness could come from unspecific forcing. And when the model is improved from 75 to 76, this feature can somehow better captured by the new generation of the model. But the model 76 still generate increased precipitation along the ITCZ because it's not like the very clear, but it still increase SAT or SAT to warming in the tropical Pacific. So then what we want to do is that, another thing I want to emphasize is that the model can all capture is the Arctic amplification. So this tells us if a model can capture is or is a kind of model can capture the AA effect in CMOS 5, like a CMOS 6 and the CSM1, but a model's waviness, like jet waviness, is not well captured. So this tells us probably something important is over here because this kind of model cannot well capture observe the rainfall change over the deep tropical Pacific. So then we try to using some method called fingerprint analysis. This fingerprint analysis is that we use like the long control run, pre-industry simulation and 1800 years of simulation, and we just try to cut this super long integration to many short consecutive 40 years period because we want to match them with observation. Observation only have a 42 years. So we just cut this long integration to many short 40 years data using some sliding window. And over each short 40 years of window, we calculate the trend of this C200 over each model segment. And we just calculate spatial correlation between each segment with observation over this box. And the purpose is that we try to see over which period a model can by chance capture like a similar waviness feature as observation over the past 40 years. So we can see here, so some period model can capture really high spatial correlation and some period is almost an opposite phase. And you can see there's like the up and down, right? This is like a decade of variability. So this is a very interesting feature. So then we want to pick up all this red star epoch minus all this the blue star epoch. The goal is that over this, the right star epoch model by chance capture waviness. And then over this period is the by chance to capture opposite side. And we do the difference of this right one and the blue one. We want to see, because we've only focused on this box, right? We don't ask a model to capture the variability over outside the box. So we want to see if a model by chance captures a similar waviness as observation, how model captured AA and a tropical forcing. So this is a composite. Do this the 23 positive right star epoch minus the 16 negative star. Let's show here. So you can see, yeah, because by design model naturally capture this because this is our goal, right? But a very interesting thing is that model also capture this the internal or not like the tropical cooling signal and this precipitation. And this is very consistent to the observation because in observation over past 40 years, we know there was a draining here and like the IPO, like a cooling. Another thing is the model cannot give us like the very strong Arctic amplification or Arctic warming effect if model can capture waviness. So by doing this test, this somehow tells us that in model world, if we want a model capture observed waviness, as shown here in this box, model always tend to get this the cooling in the deep tropics and the draining over this box. And in the observation, we find a similar thing. So this means that probably this one is a draining or is a cooling is a little bit more important than the AA to determine or to shape this waviness in the mid-latitude. So this is our finding from this simple fingerprint analysis. Then we looked at all the available real analysis, not only for ERA5, but also like the data going back to like the 1900 and 1836. We simply do like UF of a JDA V200 because the V200 can well describe this this waviness. So UF1 captures some mode over like a polar region. So we focus on UF2. So if you focus on UF2, even the period is different, but they all show very similar, like the pattern. And if you get a PC2 and we correlate it with the Z200 from same data site, and the tropical SAT data or global SAT data and the global precipitation data, we can find this mode is pretty robust, not only over the 40 years, but or even over like the 160 years. And all this mode connect to something like the cooling in the Eastern Pacific and the draining of ITCZ. And we can store time series here. They match pretty well. So this time series is from this PC2 of V200. And you can see over recent 40 years is ERA5. Means that this probably is an interdecadal mode, and the move up is an upward trend. So if you look the simple, the trend over 40 years, we find is an imprint. And if we do some like the power spectrum analysis, we can see there's the periodicity is around 40 years. Yeah, so this is my end, very close to my end of the talk. So we want to argue, probably when we talk about the mechanism of a temperature gradient, we should not only consider AA effect, we should also consider some like a tropical impact, because the gradient should consider two sides, right? And the model generates something like this. So you can see all the model get a similar thing. CMOS5, CMOS6, CSM1 all get this one. So if both warm in the tropical region and the polar region, the gradient doesn't change too much. But due to observation, due to this the internal cooling, that can favor like the decreasing of like the gradient, because that offset is the global warming generate the signal in the tropical region. So yeah, lastly we got a CSM1. We put this diabatic heating effect in the model, and this CSM1 can also generate wave train effect to some extent. So this is another approach to test the internal tropical forcing generate waviness idea. We just put diabatic heating here in CSM1, and we can see this feature compared with very similar to show some similarity to the observation. And this is another work by Teng recently, and she used some like a simple model for a tropical model, put a tropical precipitation there, can also capture a little bit feature like this wave train structure, like the high, low somewhere. This is our final slide. So I want to emphasize again, just like to understand the waviness, we need to consider like a tropical draining ITCZ, and that generates the precipitation chain here, and the wave source can disturb the jet. And the favor is the CGT establishment, and also changes and weakens the temperature gradient. So it's a takeaway message. A tug of war scenario between the forcing from tropical and from Arctic can serve as a more proper framework. So we think we should consider both rather than one side, and to understand the sensitivity of this mid-latitude circulation to like global warming and the internal variability of the climate system, and to improve our future projection of this phenomenon, we should understand both, like not only in Arctic but also in the tropical region. Yeah, I think I should stop here, and yeah, take any question or we have to answer question in the end of this session.
Thank you. We get one question here from Ray Deepak. He asked, does the Atlantic Nino, which is Eastern Equatorial Atlantic Ocean SST warming, have any effect in offsetting the CGT patterns?
Yeah, I think so. But here we haven't the chance to test that. But this is our the task we try to do in the next, because when we put the forcing here, this is a fully coupled model, so we generate some signal everywhere. So I think yeah, you are right. Probably we should keep our mind open to all possibility, and move this forcing to the Atlantic to see the response of the CGT to this forcing here, because this the jet axis reading is very close to here, so maybe the sensitivity is stronger to the forcing over that place. Yeah, thanks.
Thank you. I have one question. You show that some ensemble average trends are very different from one case observation or the analysis. In general, how's the spread of the trend in these ensemble members?
Yeah, so that's a very good question. So that's one thing we test in the end. I didn't, yeah, something like here. So we also looked at this 40-member run, and the 40-member run, we just see So the idea is that like it's a 40 member run, and we find largest spread, and even the, as a group model doesn't, if model falls by CO2 as a group doesn't do well, but it seems like some members still good and some members still like it's pretty worse, right? So we're using this same like a 40 member good member minus is a bad member. We find still show some like a cooling over here. So this indicate even in the 40 member phosphate CO2, if a model by chance capture internal cooling over like the tropical Pacific, model can still do well to capture waviness. Yeah, so this is the idea we test. I haven't show this.
Thank you. Another question from Mindy. Have you tested the impact of air quality variations and dust ash? Impact of air quality variations?
No, yeah, I haven't. So you mean like the aerosol effect? No, I haven't. Here we only, yeah, but I think there is an effect already included in the CSM1, like the CMOS 5, CMOS 6, like the forcing scenario, right? Because when the model false model by this, like the historical forcing, this effect is included in their forcing. I don't know. Maybe I need to read more paper to understand this question. Yeah, but here we don't specifically test this air quality variation and dust ashes impact. Thanks for the question.
Thank you. Yeah,
okay. Okay, thank you.
Maybe we can keep more questions in the discussion time, because we have 15-minute discussion that follow the full talk. So let's move on to keep the schedule. Our next speaker is Haileen, talking about origin of the interseasonal warm Arctic cold North American pattern. So hi.
All right, okay. So do you see my screen?
Yes.
Okay, great. 1 second.
Now it's a beautiful picture. Okay. Now
yeah. I need this. Okay. All right. So this is a continuation of this morning's session, like talking about the warm Arctic cold North American pattern. But I'm talking about the time scale for intraseasonal time scale. This is a collaborative work with Bing Yu and Nick Hall of University of Toulouse. Okay, so what I'm going to show you today, first of all, I just briefly show you what is the warm Arctic cold North American pattern. So I don't need to spend much time on this. And after that, I will show you a simple GCM simulation of this pattern, and do some analysis of the dynamical processes, mainly the interactions with time mean flow and the interactions with high frequency synoptic scale transits. All right, so the warm Arctic cold continent pattern, from this morning, we know that mainly there are two patterns. One is called the warm Arctic cold Eurasia. So that is basically there is a warm in the polar region in this area, corresponding to a cold anomaly in the Eurasia continent. And then another pattern that is in the North American sector, so that corresponding to a warm in this region in the Alaska and Bering Sea sector, associated with cold anomaly over North America. So this is from Tag et al. Shows the monthly anomaly correlation of temperature in this region and the other area. So, but today I'm only focused on this pattern, on the second pattern, on the warm Arctic cold North American pattern. So what we did is okay, I want to mention that we heard from this morning is that this pattern has different time scales. It occurs in the trend corresponding to the Arctic amplification. and also in decadal time scale and the interannual time scale and the monthly time scale. And the people are talking about, as we heard, linked this pattern to Arctic sea ice loss and warming in the Arctic as a forcing and generate some kind of response in the mid-latitude. But here, what we did is using the pentad average. Pentad, that means 5-day average over the winter season for era 5 reanalysis. No, not era 5, era interim reanalysis. So we did the EUF analysis over this region, and it comes out the first mode of variability on this pentad variability of temperature is exactly this pattern. It's very similar to what we saw for the trend, interannual variability, and decadal variability pattern. So the question I want to answer here is very simple: is do we really need sea ice forcing or some kind of external forcing, sea ice, snow cover variability, or tropical forcing to generate this kind of variability? So that's a very simple question I want to answer. The method we are using is we use a simple atmospheric model. So it's a primitive equation, AGCM. That's very similar to a Marshall-Martini model. But the basic idea is we have forcing that is time independent, that is derived from the empirically from the observational data. So that means the forcing doesn't change with time at all. It's constant. So any variability comes from internal dynamics. So it doesn't correspond to any variability in the boundary forcing. So it's internally generated. There's no moisture, no interactive convection. And we use this simple model to, we did 3,700 day integration in perpetual winter. So we took the last 3,600 days and grouped them to 5 days and look at the temperature at the lowest level, do EUF analysis, similar analysis. So the upper panel is what I showed you just a moment ago. That's from the era interim reanalysis. You see this so-called warm Arctic, cold North American pattern. And the lower panel shows the first EUF of the pentad, the lowest level of the model. That's 950 millibar. So what you can see is that it's quite strikingly that the first EUF looks very similar to this pattern, so-called warm Arctic North American pattern. You see the variance explained by in the observation is about 24%. In the model, it's about 27%. It's very close. So that means in this model, we don't need any variability. We don't need forcing. External forcing like sea ice, snow cover, the model itself internally can generate this kind of variability. So here, what I want to show you is the lead lag, like regression with PC1 of this pattern. So on the left, that's from the observation. On the right, that's from the model, the simple model. So what you can see is 3 pentad before the maximum of this this pattern. You see a negative phase of the warm Arctic, cold Eurasia pattern. I mean the negative pattern, that means it's cold there and warm here. And in the model, it also has the same, very similar pattern. So that means this kind of features not only in our observation, but also in this simple model. And here is the 250 millibar geopotential height anomaly lag regression. You see this development of this pattern, and corresponding to this pattern, that there is above normal geopotential height in this Alaska, in this Bering Sea region and negative anomaly in over North America, and very similar in the model. So, what kind of how the circulation generated this temperature anomaly? What we did, we look at the temperature advection by this anomalous circulation. We just look at the time mean temperature gradient advection. So in the observation, you see that this kind of above normal geopotential height or pressure produce this kind of cold anomaly over North America, warm anomaly over Bering Sea and this North Pacific region, and very similar features in the model. Here is the observation in the model. So that means those circulation generate this temperature anomaly by advection. So next we look at the dynamics, the interactions of different frequencies. So what we can do, we can write a variable into three components. The time mean, here is the low frequency component, and the last part is the high frequency component. The low frequency is we call the intra-season variability, and the high frequency is the synoptic scale eddies. All right, so we can look at the intra-season part, interaction with the mean flow and the interaction with the high frequency. So here is the interaction with the mean flow. We look at the kinetic energy exchange with the basic mean flow from the formula proposed by Simmons et al. So what we can see that is this zonal mean flow, zonal gradient in this region that is generate kinetic energy transfer from the mean flow to the eddies. And another thing we can look at the contribution of mean flow is we look at how the Rossby wave propagate. We look at the structure of the mean flow and calculate the so-called stationary wave number. So those shading, that's the wave number. So that means that those waves try to propagate along those maximum wave numbers. So what you can see in the observation and here in the model, they are very similar. And there's two branches of wave activity flux. One is along the northern part, that's across the Eurasia from eastern Russia to North America in this branch. Another branch is in the North Pacific, is along this kind of from the top, very similar to the PNA path of the wave activity flux. So those are very similar in this model. It's simulated. So we don't, it seems that the internal dynamics can very well create this kind of wave pattern. And finally, we look at the interaction with the high frequency eddies. So we look at the feedback from the synoptic scale eddies by look at the convergence of vorticity flux divergence by the high frequency eddies. So what you can see from the observation, and here is the model, you see that the two pentad before one pentad, this is zero, this is simultaneous. You see that there is high pressure there is a positive tendency of geopotential height. So that means the eddies is working to enforce this high pressure over this region to generate this kind of circulation that lead to this warm Arctic to the North American pattern. And in the model, it seems that the lead -1 is the strongest, but lead, simultaneously there's propagation of signals in the North Atlantic region. Okay, so to summarize, we did long perpetual winter integration and use a simple model which has constant forcing. This is important message is there's no variability. So the atmospheric internal dynamics is the only source of variability. So this study just indicate atmospheric internal dynamics alone can generate this kind of warm Arctic, cold North American pattern. Our diagnostics show that the barotropic kinetic energy conversion from the mean flow contribute, and also the barotropic feedback from the transients also contribute to this warm Arctic, cold North American pattern. So my main take-home message is that the atmospheric internal dynamics alone can generate this pattern, but I'm not exclude that the external forcing from, for example, the sea ice loss and other can also generate this pattern. But this is just a proof that that's not the only like forcing that can generate this pattern. So this is based on the recent, it's in press, very recent paper we published. We will be is accepted in Journal for Atmospheric Science. Okay, thank you very much.
Thank you, Hai. We got one question here from Yu Ru. He asked, does interaction occur mainly horizontally or also vertically at the different heights? I don't know what's the interaction. Does the interaction occur mainly horizontally?
Okay, so that means probably there is some convergence from the vertical. Yeah, those kind of patterns, they are mainly in barotropical, equivalent barotropical feature. That means every level, the structure are quite similar, the distribution. So probably the main contribution is the horizontal convergence. The vertical, there could be quite minor, if there is any contribution. Thank you, Yu.
Yeah, no more question. Yeah.
Right?
Oh, another one from Tsinghua. How does the same mechanism work over other regions?
Oh yeah, that's a very good question. It will be very interesting to look at the similar things over the Euro-Asia continent. Probably that's our next work. We should look at it. But I agree that that's must be a very interesting topic to look at. Thank you.
Thank you. No more questions. Okay, so as scheduled, we have a 10 minutes break till 3:50. So we still have a 6 minutes left. Maybe you can take a break, and we'll see you again in 6 minutes at 3:50 Eastern Time. Thank you. Hi, Yusen Liu from Beijing. Are you there?
Yes, I am. Thank you.
Oh, thank you very much for giving the talk in the middle of the night. Would you like to try to see whether you can share a screen?
Okay.
Still loading.
Yeah, I'm sorry. It froze. Okay. Can you see it?
Not yet. Yeah, looks good.
Okay. Thank you.
Yeah, thank you. Okay, welcome back to the session. Our next speaker is Patrick Delsey, talking about large-scale atmospheric and marine features connected to interannual and interdecadal fog variability in Atlantic Canada. So Patrick, please. That looks good.
Yep, you can see the full screen.
Yes.
Okay, perfect. Okay. All right, so yes, today I'm going to be talking about marine fog in Atlantic Canada. First, I'd like to acknowledge the funding and the data sets that were needed to accomplish this project, or still needed actually. So NSERC, NEOPAR, and TOST in particular for the funding. Marine fog and clouds over the ocean can significantly affect the global radiative budget. As you can see on the satellite imagery on the side that's from just a couple hours ago, the clouds and ocean are quite different in their reflectance. The albedo is very different, so it can significantly affect the amount of energy that's absorbed by the Earth, which is not necessarily true when you're over some other types of surface. And also in the past 60 years or so, if we're looking at various sites in Atlantic Canada, we're seeing trends that are actually negative for fog in most of the sites. In some places, it's not significant, such as St. John's here, where the green line, I'm talking about the fog here, the green line, which is pretty much steady over time. There's a lot of variability as well interannually, which makes it non-significant, even though the average number is decreasing a little bit. And also Sable Island has an increase in the low visibility times, less than 10 kilometers, but in terms of fog, which is below 1 kilometer, everything is going down. So I studied that, but also the interannual end cycles in the fog, and it's still ongoing. So the data sets that we used were the airport hourly observations, which start in 1953. The graph I showed earlier was up till 2017. We're still working into updating it to 2021. And I'm focusing on the 6 sites that are south Newfoundland and the Maritimes. The fog is different in its mechanism, more up north, so that would be for another project. And I'm going to show today reanalysis data obtained from ERA Interim starting in 1979, but there's current work ongoing to extend that farther in the past with the NCEP data set and the Japanese Meteorological Agency data set that goes back into the 50, which works a little bit more to cover our entirely hourly observation data set. And we're also using the HAT-I SST data set, which extends very far in the back in the past. Our fog in Atlantic Canada is mostly advection fog, especially over the water. It consists of warm, moist air that forms over the warmer waters and moves over a colder surface. In general, that colder surface can be colder water, sea ice, or snow cover. In our case, it's cold waters. And once this this warm and moist air cools down sufficiently, it starts condensing from the bottom, and a fog cloud forms and extends upwards. So in Atlantic Canada, we have the meeting of a Labrador Current, that's cold water, and the Gulf Stream south of it, which sets this contrast in temperature of the different surfaces. And in the summer pattern favors southerly winds, which blow from at the surface from the Gulf Stream to over the colder waters, which is favorable for fog formation. We can see here from the reanalyses, I highlighted here in colors the probability of high pressure. So surface sea level pressure being higher than 1020 hectopascals, and you can see the strong presence of high pressure over the Atlantic, over the in the subtropical region, which drives clockwise around it winds from the south, and it's less present in the other seasons of the year. So it's not really half a year, it's more like a quarter of the year where this is actually happening. And this drives a fog seasonality, which differs from different locations, but generally speaking, it's in the middle of summer, or maybe shifted a little bit early, since we tend to have a bit more contrast in the water temperatures earlier in the year, more into the spring than late in the summer. So you can see, generally speaking, May through August are the foggiest months of the year, but it differs depending on the location of the site. If we're zooming in on 6 of those locations, we can see maybe a little bit why. Like if we look at Sydney, Nova Scotia here, and St. John's, Newfoundland, when the wind is favorably blowing from the south, it goes over a lot of land mass. So the fog either tends to dry out or elevate into a low stratus cloud instead of maintaining itself as fog at the recording site. So that's why their fog season is a little bit offset, because the summer circulation is actually not that favorable for fog over there. The other places also have a landmass which causes a sensitivity with wind direction, but Sable Island is what we call a neutral territory, where whether the wind is coming from the south, the north, the west, or the east, it doesn't really matter. We've seen from previous findings from other talks, and a poster also from the CMOS that I've seen, that the landmass, although it's so narrow, it still affects the fog at Sable Island. It tends to elevate it a little bit, but it's still the most neutral territory that we have out of those sites. So considering we have 2 main drivers for the fog in Atlantic Canada to study the interannual and long-term and large-scale, especially variations, I developed indices. The first one being based on this, the Bermuda High here that sits on the North Atlantic. So I took 2 different points and subtracted the mean sea level pressure at both of those points. That's a little bit like the NAO is calculated, with the point being on Iceland and Portugal or something like that. And so this actually is a bit of a proxy to quantify the amount of moisture advection and heat advection from the south. The points could be a little bit in a different position, but those are a little bit arbitrary. So it essentially captures the intensity and the western extent of the Bermuda High over the year. And if we plot that as an annual mean, which are the thick lines here, the Bermuda High Index, BHI, is the orange line here. And we have the total fog hours at Sable Island, which we kept, we're going to focus on since it's our neutral territory. We can see that many of the peaks are matching. So we're capturing some sort of interannual variability. And I also plotted in the dashed line only the months of May through July to focus on the fog season. It doesn't seem to be working as well when we focus on only the fog season. So we're still getting a correlation coefficient of 0.574, which is decent, and p-value pretty low, which makes it significant for interannual variability. If we look at a longer running mean to see if we could capture the decadal variabilities, it looks like the peak in the late 80s of fog is matching with the peak in the Bermuda High Index. However, the other peak that's happening in the mid 2000s is not captured by the index. So this index seems to be more reliable for interannual variability compared to the multi or decadal variability. Now, the other mechanism is that contrast in temperature between the cold and warm waters just south of Atlantic Canada, just south of the Maritimes. This is similar to the zones that are that are used for the ENSO index. So we're subtracting the mean temperature over roughly the warmer waters of the Gulf Stream and the colder waters at the end of the Labrador Current. And if we look at the annual mean, once again, I have the plot down here. So that's a similar way that we plotted the Bermuda High Index. We can see in this case that the peaks don't match as much as the previous one. There's some moments where it does, but there's still a much higher correlation coefficient, and mostly because it captures the decadal variations. So if we look at the 5-year moving mean and the 10-year moving mean, now the peaks are matching surprisingly well. So we're capturing both of the peaks from the one from the 80s and the one from the 2000s. So this one seems to be working a little bit better in terms of decadal and long-term variations instead of year-by-year changes. And obviously, I think if we really want to investigate whether we're capturing a long-term oscillation here, that's one where we could really use a longer data set in the past to really see if it's actually a cycle or only 2 little bumps that happened before really calling it a cycle. So this could definitely be improved right now, and that's what we're working on at the moment. And obviously we have 2 indices, so we can combine them to make a stronger one. Here's the combination of the Bermuda High Index and the difference in sea surface temperature combined in a weight that makes the match better. So roughly 3 times more mass, more weight for the sea surface temperature index compared to the Bermuda High Index, and we're getting a correlation of 0.76, which is preliminary because it will change when we change the data set. But for now, it seems pretty promising, and we can see that mostly because the sea surface temperature is stronger in the combination. It's more weighted. We're getting pretty much the same result there in terms of 5 and 10-year running mean. So in terms of preliminary conclusions, because we're still working on that and still changing, the fog frequency trends are generally negative in Atlantic Canada, so we're seeing less and less fog. The Bermuda high intensity and its western extent seem to correlate well with interannual fog probability or variability, and the difference in sea surface temperature between the cold and hot waters seem to correlate better with the decadal variations. And if we combine the indices for now, it's correlating really well at 0.76. And our current work is to extend those data sets to have a bit of a stronger conclusion there, and maybe see if it's really actually a cycle, and also remove the trend and the monthly climatology in our because if we talk about to focus better on the interannual and interdecadal analyses, removing the trend would be important, since it's probably increasing our correlation a little bit for now, since both are trending in the same direction. And that's all I got for today. I'll take some questions.
Thank you, Patrick. We have one question here from Peter Taylor. Any comments on the diurnal cycle in fog frequency? And he also listed that Isaac in 2020 has a paper present on Sable Island, but not over Grand Banks.
The question is about the
diurnal cycle.
The diurnal cycle. We were looking at longer. I did see the diurnal cycle at Sable Island, and it does that. That's why I mentioned it's not a perfect place to say that we don't have land effect, but our focus was really on the annual mean. So it's mostly like what makes a foggy year rather than a less foggy year. I'm not sure if something is really affecting the diurnal cycle from what I worked on.
Yeah, another one from High Lane asking, is there feedback? Oh, I'm sorry, Peter Taylor, go ahead. Sorry.
No, I was just going to comment that George Isaac found virtually no diurnal cycle in fog out over the Grand Banks.
Yeah, that was pretty surprising, but yeah, it's surprising to me that and I saw the poster from Jackie Chen, I think,
Yeah,
earlier. Yeah, something like that. The amount of warming that's coming from the tiny crescent of the island seems to make a big difference. But yeah,
yeah.
it's definitely interesting. I don't know if it really affects the yearly total number of hours, but it's definitely something interesting that I did not look into in this project.
Thank you. Another question from Haileen asking, is there feedback of the fog to atmospheric circulation? Yeah, the other way around, I guess. I looked at it the other way around where I felt like the atmospheric situation was affecting the fog, but obviously it's a little bit coupled. So the fog would probably decrease the surface temperature because it blocks, so it would maintain its environment. That's an interesting question. I don't know if I can necessarily give a good answer right away like that, because it could be the other way around, that the fog decreases the surface temperature just because it's blocking a bit of sunlight. I don't know if I could necessarily distinguish which one happens first. Yeah, that's all I can tell you about. Thank you. Another one from Matt Grinter. Are there any indication as to why the frequency of fog is decreasing over time?
It seems to be mostly because the sea surface temperature of the cold waters around the Labrador Sea is warming up faster than the warmer waters, probably a little bit associated with the Arctic warming up a little bit faster than the rest of, or than the subtropical latitudes. So what I'm seeing when I look at the trends without the interannual variability, it looks like, and it's projected in the future to remain like that as well, that the colder waters are warming up faster. So we're reducing the difference between both, and therefore reducing the condensability of the cold waters.
Thank you. I think we should move on, keep the schedule. Our next speaker is Yusen Liu, talking about the North Pacific blob acts to increase the predictability of the Atlantic warm pool. Thank you, Yusen, for giving the talk in the middle of the night.
Can you see the screen now?
Yeah, it looks great.
Thank you, Professor, for giving me such a great opportunity to present our work. The North Pacific blob acts to increase the predictability of the Atlantic warm pool.
Maybe you can show it in a full screen mode. Yeah, thanks.
The presentation contains the following sections, and I'm just going to start. So firstly, I'm going to introduce you the Atlantic warm pool. The Atlantic warm pool was first proposed by Wang in 2002. It is defined as the region where the sea surface temperature exceeding 28.5 degrees Celsius. And it is a part of the Western Hemisphere warm pool, which happens to be the second largest warm pool in the world. And it has strong seasonality, as shown in the figure. It reaches the maximum intensity during the summer and autumn. The Atlantic warm pool has a wide range of impact on our climate. For example, the small-scale sea breeze over the coastal region and the continental precipitation in North America and the moisture transport in Central America. It is also an important factor on hurricane activity in North Atlantic because the warm SST may influence the genesis, frequency, and duration of hurricane activity. It is also suggested that the AWP leads La Nina for 1 year. And it is also interesting that the Eastern Pacific ANSO is able to influence the Atlantic warm pole variability through the changes in water circulation. And it is enhanced and maintained through the local SST long wave positive feedback. But the relationship between El Nino and the AWP also have uncertainties, since the strong El Nino doesn't always guarantee a warmer than normal warm pole. So the question remains, is ANSO the only remote factor on interannual timescale? And can we extend the AWP predictability beyond half a year? And as previous study mainly focused on the tropical factors, and we wonder if there's any extratropical signals that plays a role in the development of the Atlantic warm pole. While over the North Pacific Basin, the prolonged sea surface temperature warm extremes called the marine heat wave occasionally taken place in this region, and it has a nickname called the blob in North Pacific. And previous study mainly focused on the wintertime blob, which, such as the one in 2013, 2015, which has a anomalous SST in 2014 winter, that the SST anomaly even exceed 2.5 degrees Celsius. Actually, we found out that the blob not only taken place in the winter, we find a lot of historical summer blob since 1950. So in this study, we mainly focused on the summer blob, which has been rarely studied. The North Pacific warm blob has significant impact on the marine ecosystem as well as the local fishery, because the warm temperature is not good for the fish to grow, and it also impacts the local economy. Other than that, we can also find the North Pacific warm blob is connected to the extremely hot weather event in North America. There are also studies that suggest that the wintertime blob may trigger El Nino in the following year. As previous study mainly focused on this case study, we would wonder what is the regular impact of summertime blob on climate and weather patterns that has not been fully understood. Previous studies suggest that the Central Pacific SST anomalies may modulate the atmospheric circulation of the mid-high latitudes, which then leads to anomalies in sea surface temperature over the extratropics. The extratropical SST signal may propagate back to the tropical Pacific. And this process is called the extratropical-tropical interaction. Moreover, it is also a very popular topic of three ocean basin interaction proposed by Wang in 2019. And we may find that the interactions or teleconnection patterns between the North Pacific and North Atlantic are very active. So we wondered, what role does the blob play in the tropical, extratropical, Pacific Atlantic teleconnections? And if the blob and the AWP are connected, and if so, what is the mechanism? So according to previous study, we defined the AWP index by the area weighted average of SST anomalies in the AWP region shown in this figure. And through regression analysis, we found that the SST, the preceding summer SST in the Northeast Pacific, where the blob taken place, show a very strong connection with the AWP with 1 year lead. So we infer that the blob may lead the AWP 1 year ahead. So through correlation analysis, by calculating the correlation coefficient between the two index, while the blob index leads the AWP index by 1 year, we found the correlation coefficient is reaches 0.68. That further indicate the relationship between them is robust. And as they connected together, we wonder how the blob as the warming signal propagates or influence the AWP SST variability. The correlation map between the preceding summer blob index and the SST anomalous in the following season show a clear SST propagation from the Northeast Pacific to the tropical Central Pacific from preceding summer to throughout the winter and reaches the maximum intensity in the spring of the Central Pacific. And at the meantime, the Atlantic warm pole starts to warm since winter and reaches maximum intensity in the summer in response to the preceding blob signal. So we may determine three key regions, that is the blob, the tropical Central Pacific, and the AWP region. So to calculate the lead-lag correlation between the preceding blob and the Central Pacific AWP index over different seasons, we find significant warming tendencies over the Central Pacific from the preceding autumn to spring in response to the preceding blob signal. And we also find a similar warming tendency of the Atlantic warm pole that starts to warm since winter and reaches maximum intensity in summer. So it is likely that the blob signal propagates to the tropical Central Pacific, and for some reason, the AWP warms in response to the preceding blob signal. We also conducted a North Pacific pacemaker experiment with observed monthly SST prescribed in the Northeast Pacific, and the rest of the places are coupled to a Sabelson model to reproduce the air-sea interactions outside the blob region. As shown in the figure, the blob signal propagates towards the tropical Central Pacific from preceding summer to spring, and we can also see the development of the SST anomalous in the AWP region from winter to the summer. So it is also consistent that there are two warming tendencies over the Central Pacific and Atlantic warm pole in the model simulation. And those two warming tendencies has a time lag of approximately one season. So we may infer that the preceding blob signal propagates to tropical Central Pacific, and then it influences the Atlantic warm pole. To determine the role of Central Pacific SST, we calculated its correlation, the wintertime Central Pacific SST. We calculate the correlations between the blob and Central Pacific as the correlation coefficient, which is 0.59. And we also calculate the correlation of the wintertime Central Pacific SST with the following AWP SST variability. The correlation coefficient reaches 0.54. So it is likely that the Central Pacific SST play an intermediate role that transmit the blob signal to the following AWP. As we all know that the Central Pacific SST has significant resistance from summer to winter. So is it likely that the summertime Central Pacific SST dominate the blob and also influence the AWP? To rule out this possibility, we calculate the partial correlation. As we remove the summertime Central Pacific SST, the correlation between blob and AWP remains, and it reaches 0.58. And when we eliminate the influence of the preceding summer blob signal, the Central Pacific SST is not correlated with the following AWP. So it is conclusively proved that the Central Pacific SST may play an intermediate role between in the teleconnection between the blob and AWP. But there are still questions remaining unexplained, that how the preceding summer blob signal propagates towards the tropical Central Pacific, and how the AWP warming develops and maintains. What triggers the SST warming? And why the warming tendency in Central Pacific leads that in the AWP by approximately one season. So to understand the mechanism, we calculate the sea level pressure and wind anomalies regressed onto the preceding blob signal. It turns out that the seasonal footprint mechanism can well explain the SST propagation from the Northeast Pacific to tropical Central Pacific. As shown in the figure, the blob-related warm anomaly induces low pressure over the subtropics and induces the westerly anomalies in the subtropics, which significantly weakens the predominant subtropical trade winds, which suppress the local evaporation and the latent heat release. So the SST warming signal may be able to propagate equatorward together with the low pressure and the westerly anomalies. And in this case, through the seasonal footprint mechanism, the blob warming signal can propagate to the Central Pacific from preceding summer to winter. And it is also worth noticing that there's a low pressure that develops in winter over the AWP region, which is critical to the formation of the warm pole. But how this low pressure is connected to the propagation of the North Pacific basin? And we found out that during the winter, the SST, the blob signal propagates to the Central Pacific. That leads to the Central Pacific warming, which then excite the PNA pattern, the Pacific North American pattern. And interestingly, at the downstream of the wave train, there's a low pressure cell over the AWP region, which explains the formation of low pressure. This low pressure over the AWP region excites the local cloud long wave radiation SST feedback. As the low pressure excites the ascending motion and increase the local cloud cover, there's more long wave radiation that back to the surface that heats the underlying surface. And this is also proved by the radiative data. As shown in the figure, this is the regression map of the long wave radiation from spring to summer in response to the preceding blob signal. The long wave radiation has a net warming effect. And as shown in this chart, the long wave radiation dominates the warming, while as the increased cloud cover have damping effect due to the reflection of short wave radiation. But it turns out we found that the short wave radiation has the cooling effect is weaker than the warming effect. So the net effect is warming in association with the cloud long wave radiation SST feedback. So based on that mechanism mentioned about, we found that the blob and the AWP has strong correlation, and they have, more importantly, they have a 1 year time lag. So based on the blob, we can construct an AWP prediction model as shown in here. And using the k-fold cross-validation method, we can calculate the hindcast results based on the blob. It is suggested that the hindcast results is highly coherent with the observed AWP SST variability, with a correlation coefficient which is 0.76. So it is proof that the prediction model of AWP based on the blob, based on the preceding summer blob, can significantly improve the predictability of the AWP. So to summarize this, the relationship between the North Pacific summer blob and the AWP is robust, which tends to increase the predictability of AWP 1 year in advance. And the linkage between the blob and AWP enriches our understanding about the extratropical, Pacific, Atlantic teleconnections. And as a marine heat wave, the blob is projected to intensify in a warmer climate. So it is interesting to find out what is the teleconnection change in the future, and it needs further investigation. We also investigate the role of ANSO played in the blob and AWP teleconnection. It turns out we found that even with the preceding winter, El Nino is removed, the correlation between blob and AWP is still robust, with the correlation coefficient reaches 0.58. Also, the ANSO-based prediction model is less skillful than the blob-based prediction model, as the coherence between the hindcast and the observation is only 0.45. It is also worth noting that our North Pacific pacemaker experiment uses a slab ocean model, which doesn't contain any ocean dynamics. So it may partly rule out the role of ANSO played in this teleconnection pattern, but we may not fully rule out the influence of ANSO, but it could be investigated in future study. And this is all about it, and thank you for your listening. Any questions?
Thank you very much. Yeah, we have no question in the chat yet. I have one question. Do you have any idea what's responsible for the formation of the summertime North Pacific blob? Or in other words, is it driven by any specific atmospheric circulation?
Thank you for your question. This is a very interesting question. There's a lot of study that studies the formation of summer blob. In fact, there's one article on the Nature Communications by Maya in 2020 that analyzed the formation mechanism of the marine heat wave in the summer of 2019. It is suggested that the weakened subtropical North Pacific subtropical high is probably a dominant factor that influences the formation of the blob, while the NPSH, the North Pacific subtropical high, may be related to the subtropical SST and the Central Pacific SST. So it is mainly regulated by the atmospheric force.
Thank you. We have one question from Tsinghua. Oh, sorry. Yeah, okay. This is first, maybe. Nice talk. Is the AWP a part of the AMO? What's the role of the AMO in shaping the framework you just proposed?
Well, thank you for your question. I believe the wormhole is mainly located over the Gulf of Mexico and the Caribbean Sea. So geologically is a little different from the patterns of AMO. Also, in this study, we mainly focus on the annual time scale. So the AMO may be a dominant mode of the multi-decadal time scale. I believe the difference in time scales may be distinguished in this work.
Yeah,
so,
another question from Hailen. He asked, how does the scale of your statistical model compare to a dynamical model?
Well, we didn't try our dynamical model, which would be more complex, but we believe the statistical model just on the one hand proved the statistical model can prove that the relationship between them is kind of robust. But it would be nice to check the dynamical model to make further practical AWP prediction.
Thank you. Another one from Lu Yu. He asked, the delay time of AWP relied on blob, exactly 1 year or number of months?
We calculate based on seasonal, like this is the seasonal mean of the preceding summertime SST. So we didn't technically know the exact number of the lead mounts, but we believe they have approximately 1 year lead between them, and summer to summer.
Okay, and another question from first, Mindy has a comment that she likes your graphs, and also she asked how's the PDO and the blob related? They seem to be the same thing.
Well, yes, this is more like the formation mechanism of blob, and recently we've been calculating that the correlation between the IPO and the blob is 0.18, I suppose. But I know the patterns were kind of similar, but the correlation between them seems not that robust. But we believe it may contribute to some extent.
Thank you. I have one more question. It seems to me, if I remember correctly, like several years ago, Professor Jin Yu, he studied and then he found that this like a North Pacific blob is highly related to TNH pattern. Is that right? Something like that. Maybe you can check. I think I published in 2017 or 18, like Climate, General Climate, and it's a very nice mechanism proposed there as well. Maybe it's a bit different from what you are looking. It seems he look at the like extratropical relation between Pacific and Atlantic.
Exactly.
Mm-hmm. Thank you.
I believe there's no questions.
Okay,
So
we have been scheduled 15-minute discussion time here. So I think that the above presentation show very interesting remote and local atmosphere-ocean influence on climate variability, as well as the intercontinental and interbasin interaction. So any further question or comment on these talk or on relevant topics? If there's no question or comments, then maybe we can take a break, and then there's a third part of this session start from 4:50 or 4:55. Yeah, 4:55 Eastern time. So you're very welcome to join next session at 4:55 Eastern time. Thank you very much for all the speakers, technical assistant, and the audience for joining this session.
Thank you very much.
Thank you.